Welcome to Chapter 5, Discrete Probability Distributions. This is the first chapter on probability distributions, and we will have another one coming up after this. So, first of all, to kind of recall, we've been talking about variables and probability, and so now we're going to define a random variable as a function that assigns unique numerical values to all possible outcomes of an experiment. Okay, so we've been assigning probability values to outcomes of doing something like rolling a dice, and so a random variable is a function that does that, helps us assign probabilities. So there are two types of random variables. There are discrete variables and there are continuous, and this should sound very familiar. We've talked about categorical variables or discrete numerical variables. And so here discrete means that the values are either whole numbers or they are a limited, that is finite, set of numbers. And then continuous variables, which will be the next chapter, are those that can take on any value and have an infinite number of possible values. So an example of discrete variables is when we roll a six-sided die, or D6. If we pull a colored ball out of a sack and we want to know what color it is, if we pick a color out of a set of colored marbles and we record what color it is, if we test a part in manufacturing and we say either the part is good or the part is not good in some way, yes or no, that's a discrete variable. If we have a set of products or advertisements and we ask you to pick the one that you prefer or that is your favorite from those, that's discrete. And an admissions decision to college, you get admitted or you don't get admitted or you get waitlisted, those are discrete variables. So we've talked about all of those kinds of variables before. Now we're going to make them do a little bit more work. Some properties of discrete probability distributions. As before, the probability of everything has to be between 0 and 1. And 0 means it's impossible, and 1 means it's certain. And most things have a probability somewhere in between that. The sum of all the probabilities of all of the different x's, the different outcomes, has to be 1. So that's not any different than what we've been talking about. And here are some examples. We know with the coin toss that you're going to get either heads or tails, and the probability of each one is 50%. So you can see these bars are at the 0.50 level. If you toss a 10-sided die, or a D10, then you could get a 1 or 2 or 3 or 4, etc., up to 10, and each of those has a probability of 1 over 10, or 0.1. So you can see all of these bars come up to the 0.1 probability point. And now we're going to want to ask, what are the descriptive statistics for this distribution? So remember, we've had the normal distribution, and we've talked about the mean of that being the center, and the standard deviation being how dispersed it is. And so now we're going to be able to talk about the mean and standard deviation, well, variance and standard deviation for discrete random variables. The mean, or the average, the arithmetic average, is also called the expected value. So this is sort of like if you repeat it over and 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 over, sort of on average, what do you expect the result to be? So we write that with a capital E, E for expected value of x, is the mean, and it is the sum of the value x times the probability of getting that value. Okay, so it's every outcome weighted by the probability of that outcome. The variance, or sigma squared, is the sum of the x value minus the mean squared, and so this is how we always start this, but now for each value of x we're going to multiply by the probability of that value. And this equation simplifies, and this is definitely a big help, to the sum of x squared times p of x. So for each x, you take the value and you square it, and then you multiply it by the probability of that value. You add all of those up, and then you subtract the mean, but you square it before you subtract it. Okay? And then once you have the variance, of course, the standard deviation is the square root of the variance. So that's like it always is. Here's an example for a six-sided die, or a D6. Remember the space, the sample space is, you can get a 1, 2, 3, 4, 5, or 6, and the probability of each outcome is 1 over 6, and the expected value, let's look back, the expected value is the value times the probability of that value, and then you add those all up. So the first value we could get is 1. The probability of getting a 1 is 1 over 6. The next value you could get is a 2. The probability is a 1 over 6. 3 times 1 over 6. 4 times 1 over 6. 5 times 1 over 6. And 6 times 1 over 6. And if we multiply these out, we get 1 over 6 plus 2 over 6 plus 3 over 6, etc., which is 21 over 6, which is 3.5. And that's also the median, right? Because the median is going to be halfway between the third and the fourth point in this case, which is 3 and 4. So that's the expected value, is a 3.5. The variance for that, remember we said the shortcut way is to take each x and square it, and then multiply it by the probability. We're going to add all of those, and then at the end subtract mu squared. So we're going to take each value. So there's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And for each one, we're going to multiply it by the probability, which is 1/6. So we'll get 1/6 on each of these. Then at the end, we're going to subtract the mean that we just found, the 3.5 squared. So if we multiply these out, we get 1 over 6, 4 over 6, 9 over 6, etc. And the 3.5 squared is 12.25. So we're going to subtract that. If we add all of these, we end up with 91 over 6 minus 12.25. And that turns out to be 2.92. And then that is the variance. And the standard deviation is just the square root of 2.92, or 1.71. Okay, so the expected value, or mean, of this distribution is 3.5, and the variance is 2.92. So there are three important discrete probability distributions: the binomial, the Poisson, and the hypergeometric. The first one we're going to talk about is the binomial distribution, and here are a bunch of people in China, and that's going to be important to our example. So a binomial distribution is one that only has two outcomes, and the outcomes are classically labeled success or failure. Now it could be a yes and a no, it could be an up or a down, it could be an in or an out, it could be anything as long as there are only two of them. Okay, and you label whatever you want success. The probability of success has to be the same for every trial that you do. So every time you do whatever you do, the probability of success has to be the same. So we're going to let x be the number of successes that we have in n trials. And so you can think of this like, I'm going to toss a coin and I'm going to bet heads. So a success is it comes up heads. And I'm going to toss the coin 10 times, and if I want 8 heads, then x is going to be 8. It's like, how many heads do I get in my 10 trials? And the example we're going to do is one on international travelers, also known as How I Almost Lost Bonnie in China. And this really did happen. I took a group of MBA students to China on a study trip, and one of them went wandering around in Hangzhou, and we were afraid that we had lost her because we couldn't get in touch with her via cell phone, and we had no idea where she went. So that was an adventure. Now, in this case, I'm actually going to say that for international travelers, venturing out on their own is a success. And the reason for that is because if you always stay with the group and always stay on the path, then you don't learn anything outside of the box. And it's actually good to, take a little bit of a chance and meet some new people and go exploring on your own a bit. That's part of the whole going abroad experience. So we're actually going to call that success. And if a student stays with the group all the time, we're going to call it failure, even though Bonnie did almost give me a heart attack in China. And we're actually going to say that the probability of any given traveler venturing out on their own is going to be 77%, or 0.77. Okay, so success, the student goes on their own. Failure, they stay with the group. Probability of success, 77%. Now, the first thing we've got to think about is how many different ways could we get a success in end trials? And that is a combination like we did in our last probability chapter. And so that should look really familiar. That is n factorial over x factorial times n minus x factorial. And then we have the probability of x successes on n trials, which is the probability of success raised to the x times the probability of failure times raised to the n minus x power. There we go. Too many times in powers here. And we're going to do an example on this because that is definitely hard to look at all of that stuff flying around there. So what if we have three travelers we're interested in, Bonnie, Mel, and Kate? What is the probability that two of them will venture out on their own? Now, the first thing we do is figure out the number of outcomes that can provide X successes in N trials. And we have three students here, so we have N is 3, right? Any one of those could go out on their own. So there's sort of 3 chances. And then we want to know the probability of 2 of them going out on their own. So that would be 2 successes out of 3. So we have the combinations is n factorial over x factorial times n minus x factorial. And so for 3 and 2, that's 3 factorial over 2 factorial times 3 minus 2 factorial, or 3 factorial over 2 factorial times 1 factorial, which is 3 times 2 times 1 divided by 2 times 1 times 1, which is basically 6 divided by 2 is 3. So there are 3 ways this could happen. So now think about this. So we have Bonnie, Mel, and Kate. Bonnie and Mel could go out venturing on their own, or Bonnie and Kate could go out venturing on their own, or Mel and Kate could go out venturing on their own. Okay? So those are the 3 ways that it could happen. Now, we figured out that there are 3 ways, but what's the probability of any one of those combinations? So recall that the probability of one of them venturing out is 77%. So the probability that someone doesn't is 1 minus 77%, or 23%. Okay? So let's think about, like, if Bonnie and Kate do and Mel doesn't. Okay, that would be 2 successes out of 3. So the probability of that would be 0.77 for Bonnie going out times 0.77 for Kate going out times 0.23 because Mel does not go out, right? So this is Bonnie goes out and Kate goes out and Mel does not. Okay? So 77 times 23 gives us 0.136. All right? And the formula for this, again, is p to the x times 1 minus p to the n minus x, or p is 77, so here's your 77, and there were 2 of those, so squared, times the complement, or 1 minus 77, and there were 3 minus 2 of those, okay, or 1, so we get 0.77 times 2 things, or raised to the 2nd power, times 0.23 just raised to the 1 power because there's only one student not going out. And that gives us 0.136, or about 14%. Okay? Here's another way to look at that, is with a probability tree. So here's where we're going to start, and people are going to make decisions. And first, Bonnie's going to make a decision. Bonnie's going to venture out on her own, or she's going to stay with the group. Okay? And then, no matter what Bonnie does, say she ventures out. Well, then Mel's going to decide. Is she going to venture out, or is she going to stay with the group? Or maybe Bonnie decides to stay with the group. Well, so Mel still has to decide. Is she going to venture out, or is she going to stay with the group? Okay? And then Kate has to decide. So, Bonnie decides she's going out. Mel decides she's going out. Kate can decide to go out, or she can decide to stay with the group. Okay? So, or maybe Bonnie goes out, Mel stays in, Kate's got to decide. I'm going out, I'm staying in. Okay? So now, how many successes do we have for each of these? Well, here, all 3 of them go out, so that's 3 successes. Here, Bonnie and Mel go out, but Kate stays, so that's 2 successes. This one's 2, okay? Bonnie goes out, Mel stays in, Kate goes out, so that's 2. This one, only Bonnie goes out, Mel and Kate stay, so that's 1 success. Okay, so X here counts how many successes there are, and the probability is related to the 77 and the 23. So this 0.46 is 0.77, because Bonnie goes out, times 0.77, because Mel goes out, times 0.77, because Kate goes out. Gives us 46. There's the 14 that we just got when we had 2 successes. We just rounded it. It was 0.13. It was 0.136, and we've rounded it to 0.14. Okay, right there, there, and there. This one with 1 success is 0.77 times 0.23 times 0.23 gives us 0.04. We've got that there, there, and there. And then this one is 0.23 cubed, basically, which gives us 0.01. And those do total to 101 because I've got a little bit of a rounding thing going on there, but that's okay. All right? So now, if we put this all together, we have the binomial probability function. This part on the left is the number of combinations, right? And let's look. We had 1, 2, 3 combinations with 2 successes, which is what we originally figured out, right? So there are 3 ways this could happen. So this part tells us how many ways it can happen. And then this part tells us the probability, right? So for each of those 2's, the probability was 0.14. Okay, so this is the probability part. So f of x is the probability of x successes in n trials, or in this case, the probability of 2 successes out of our 3 travelers. Okay? Just a note, 1 minus p, the complement probability, is also sometimes called q. In our case, basically we have f of x is 3 times 0.14 is 0.42. So the overall probability of 2 of them venturing out of the 3 is 0.42, or almost half. Okay? The summary statistics for binomial probabilities, the expected value, or mu, is n times p. Okay? The variance is n times p, the thing you just figured out, times 1 minus p. And the standard deviation is the square root of the variance. So let's do this. Now, I'm going to tell you I actually took 6 MBA students to China, not just 3. So how many would we expect to venture out on their own? Okay, well that's the expected value, which is the mean, which is NP. So now there were actually 6 of them, that's n, times 0.77 is 4.62. I would actually expect 4 or more of them to venture out on their own out of the 6. So I guess I got off easy since Bonnie was the only one that did. Once we have this 4.62, that's NP, right? So I'm going to take that 4.62, I'm going to multiply it by 1 minus P, or 0.23, and that's going to give me a variance of 1.06. And then the standard deviation is just going to be the square root of that. So the square root of 1.06 is 1.03. Okay? So then I can get some nice summary statistics on that. Phew. Let that just sort of settle for a minute. That was binomial probability. You might want to pause, go get a glass of water or something. Okay. The next distribution is the Poisson distribution, and for those of us who speak a little bit of French, we know that Poisson means fish. Okay, so the inventor of this was not a fish. It's this guy here, but I like the fishy picture to remind us. The Poisson distribution is used. The Poisson distribution is used for examining the number of times something happens over a specific interval. So this could be how many times does something happen per hour, or this could be like how many times does something happen per mile. Okay, could be a time interval or a space interval, in other words. The results are discrete, but they may assume an infinite sequence of values, and the probability of the occurrence has to be the same for any two intervals of equal length. So that's kind of like the binomial, right, where the probability has to be the same each time. The occurrence in one interval has to be independent of the occurrence in any other interval. So that means that what happens at one time does not influence what happens in the next time interval. Okay, there's no reference to the previous. And one of the places that we use this in business a lot is for predicting customer flow or patronage of a place over time. So the Poisson probability function looks like this, and again, f of x is the probability of x occurrences in an interval, so you know how many times something happens in that interval. Mu is the mean or average number of occurrences in an interval, and that's usually given to us. And E here is it's approximately 2.71828. Technically, E is the number for which the natural log of E is equal to 1. Okay, so if you take the natural log, if you punch in your calculator 2.71828 and hit the ln function, you're going to get 1, or something pretty close to 1. So here's an example. Say we want to staff the reference desk in the library. And by the way, reference librarians are super helpful people. If you have a research project to do, or a paper, or anything, they are very, very helpful, and they're a good place to stop off early and have them help you find the information you need for your project. So on average, the reference desk, say, gets 4 inquiries per hour. Okay? And let's say that one reference librarian, because they're really sharp, they can handle up to 8 inquiries per hour. So if we think that it's not terribly likely that we're going to get anything higher than 8, then maybe we can get by with just staffing with one reference librarian at a time. But if we think it's likely that we're going to have a lot more than 8 inquiries in an hour, then maybe we need to have 2. Okay, so I mean, on average it's 4, but it could vary wildly. So the question is, what is the likelihood of getting 10 inquiries per hour? Okay, so the average is 4. The maximum that a librarian can handle is 8. And what's the likelihood of getting 10? So we need to figure out where to put these into our equation. So mu is 4. It's the average. So wherever we have mu in our equation, we're going to put 4. So we have 4 here, and we have to the minus mu, so that's to the minus 4. Okay, and then x is 10 because we want the likelihood of getting 10 inquiries. So everywhere we have an x, we put a 10. So now we've got 4 to the 10th power times e to the minus 4th power over, and here's an x down here, so 10 factorial. Remember that's 10 times 9 times 8 times 7, etc. And if we do that all out, and here's where having a calculator that will raise things to a higher power is really helpful, because you can put your what did we say that was, 2.71828 into your calculator, and you can hit your little y to the x and then type in -4 for the exponent, and you can get that. And then you're going to multiply that by 4, and you're going to want your y to the x and hit the 10th power. Or we'll figure out how to do this in Excel, because that'll be helpful. And so you figure that all out, and it comes out to 0.005. Okay, so what does that mean? That means that the probability of getting 10 inquiries is 1/2 of 1%, right? Because 1% would be 0.01. So does it look like we need to staff an additional librarian at the reference desk in case there are 10 inquiries? I mean, is it going to be worth it to pay somebody to have a whole extra librarian there? Or do we think that most of the time one can handle it? Well, 1/2 of 1% is not very frequent, not very likely. I'm thinking we can get away with one librarian here. The statistics for the Poisson distributions, the mean is usually given to us like it was in this. Remember, it was 4 per hour, so that's mu. And the variance is equal to the mean for the Poisson distribution. So how handy is that? The mean is going to be given to you, and that's also going to be the variance. Woohoo! So in our example, the mean was 4, so that's the mean. The variance is also the mean, so that's 4. And the only slight bit of work we have to do here is to take the square root of 4 and figure out the standard deviation. In this case, is 2. And that's it. We're not going to do hypergeometric distributions, although if you're interested, I'd definitely encourage you to read about that and learn some more. And this presentation is licensed 2014 under Creative Commons Attribution Non-Commercial No Derivatives version 4.0 International License. Thank you.